Alright, hello everyone. In this video I'm going to be going over the solutions to the first FRQ problem set that I assigned. This set has two problems that both deal with rotational motion, which is for many one of the more conceptually difficult topics in this course. So I will try to give clear explanations and explain my thought process going through all of these problems. So let's go ahead and get started. So in the first problem here, you're given a set of three figures. So we're looking at a person who's on a diving board, they jump off of the platform, and then as they're descending, they tuck their arms and legs in close to their body so they can start rotating, and then they extend their arms and legs once more before entering the water. And the first question here is that they want you to explain in a paragraph length response why this person will rotate faster in figure 2 than in either figures 1 or 3. All right, so if you think about it, this is sort of similar to what happens with a figure skater when they're spinning in a circle and they pull their arms close to their body. They speed up. You may remember this from the in-class demos that we did as well. So what are some of the ideas at play here? So first of all, one of the major concepts that we can apply to this problem is that of angular momentum. So any rotating object has angular momentum, which is equal to the moment of inertia I multiplied by their angular velocity. So one of the first things you'd want to say in this problem is that angular momentum is conserved. So we know however much angular momentum this person has when they start rotating in figure 1, they're going to have the same amount of angular momentum in figures 2 and 3. So the next thing we can mention is this equation that I had already written down, that the angular momentum is equal to their moment of inertia multiplied by omega, which is the angular velocity. And omega, remember, this is the measure of how fast they are rotating. Okay, so the next thing we want to address is how the moment of inertia changes from figure 1 to figure 2 to figure 3. So you want to say something that demonstrates that you understand how moment of inertia is related to mass distribution. And what this means really is that as the mass of an object moves closer to the axis of rotation, the moment of inertia decreases. The farther away the mass is from the axis of rotation, the larger the moment of inertia. So in figure 2, moment of inertia, I'll call this I2, let's call this I1 and I3. I2 is going to be less than I1 or I3 because the mass of the diver is closer to the axis of rotation. Okay, so we know in figure 2, the diver has the lowest moment of inertia. Since the angular momentum is conserved, if the moment of inertia goes down, then the rate of rotation must go up. So this means that the diver is going to rotate faster in figure 2 when they have the lower moment of inertia, and then when they extend their arms and legs, the moment of inertia is going to go back up, and the rotation will slow down once more. So the fastest rotation happens in figure 2. So as long as you address all of these points here, you should get full credit for that question. The second question asks about the rotational kinetic energy of the athletes in each of these three figures. So specifically, it's asking if the kinetic energy in figure 2, the rotational kinetic energy specifically, is greater than, less than, or equal to the rotational kinetic energy in figure 1. All right, so what we need to know to answer this is that the rotational kinetic energy of an object is 1/2 times moment of inertia times omega squared. And this is one of the formulas that you are given. recall that this has some similarity to translational kinetic energy 1/2 mv squared. Okay, so going from figure 1 to figure 2, we know that the moment of inertia goes down and the angular velocity goes up. So knowing that angular momentum is conserved, we know that the decrease in moment of inertia, if it goes down by, say, a factor of 2, then omega is going to go up by the same factor of 2. But since omega is squared, then that's actually going to give a larger change than the decrease in moment of inertia. So you can say that the decrease in moment of inertia does not make up for the increase in angular velocity. So we're actually going to have the rotational kinetic energy be larger in figure 2. All right. A couple other ways we can think about this. We can write the rotational kinetic energy like this, just grouping terms differently. So now in parentheses here we have the angular momentum, which is constant. So we can just ignore what's inside the parentheses. That's not going to change from figure 1 to figure 2, but we know that the angular velocity increases, so that means the rotational kinetic energy is going to increase. So you can explain it that way as well. All right, so that should take care of the first problem. So now let's look at the second one. All right, so in the second problem, we have this rotating disk, and we're asked some questions about its angular velocity and angular acceleration as a function of time. So in part A, it says, at time t equals 0, the disk has an initial positive angular velocity, and then it comes to rest at time t1. And then you're given this graph here, and we're asked to sketch a graph that could represent the angular velocity as a function of time from 0 to t1. Well, it tells us in the problem that the initial angular velocity is omega 0, so the graph has to pass through this point here. It comes to rest at time t1. So at t1, that's the far right of the graph. The angular velocity must be 0, so it must pass through this point here. Now, the problem tells us that we have a constant torque. So what does that mean? Well, we know torque causes angular acceleration, just like force causes acceleration. So constant torque means we have a constant angular acceleration. In other words, this disk is going to lose speed at a constant rate, which means we have a straight line connecting these 2 points. So the graph for angular velocity should look like that. All right, the next graph is angular acceleration. We just said that that is constant, so that should look like a horizontal line. We also know that angular acceleration is equal to the slope of angular velocity. So if I look at the graph I just drew on the left, the slope of that is negative, so I should have a constant negative value of angular acceleration, so maybe something like that. It doesn't matter where you actually draw it, if you draw it on this grid line or this grid line, any of those would be fine, as long as it is a horizontal line with a negative value, you get full points for that. Okay, so part B asks you to derive an equation for the rotational inertia of this disk in terms of 3 variables. And those are the torque, which we call T0, the initial angular velocity omega 0, and the time T1. All right, so there's a couple of ways we could do this. One is we could use the definition of torque. Torque equals I times alpha. This is Newton's second law for rotation. So if we fill that in, the net torque is just T0. I is what we're trying to solve. So what is the angular acceleration? Well, the angular acceleration is defined as the change in angular velocity divided by the change in time. So the angular velocity changes by an amount omega 0, and the time interval is just equal to T1. So we have this equation. We want to solve for I, so we just rearrange things and we get this expression here. Now you may notice technically I left out a detail here. The change in omega is actually negative, so you might argue that there should be a minus sign here and a minus sign here. They will actually accept either answer on this problem, so you don't have to worry too much about that. If you just want to work with magnitudes and say all of these quantities are positive, that's fine, as long as you know that I has to be a positive value, just like mass has to be positive. All right, so that's the answer to part B. All right, so part C says that now we're going to repeat this experiment, but this time we're going to let oil drip on the surface slowly, starting at the time half of t1. So things are going to go just as before for half of the time interval, but then after that we're going to start dripping oil on this disk so that the friction is gradually reduced over time. And we have a new set of axes that we want to fill out to show how the disk is going to behave in this second experiment. So the first thing we can say is that nothing different is going to happen for the first half of this time interval because the oil has not started dripping yet. So the graph should look identical to our first graph for half of the time interval. So now the question is, what's going to be different starting at time half t1? So if oil is dripping on this platform, that's going to reduce the friction, which means the wheel is not going to slow down quite so much. The friction, remember, is the thing that is causing the wheel to slow down. So if there is less friction, then the wheel would continue spinning for longer than it normally would. It's going to take more time to slow down. So, if this dashed line shows what would happen without the oil dripping, what's actually going to happen is something like this. So the line is going to start bending upward. So it's going to maintain more angular velocity for a longer period of time. And it's going to take more than the original amount of time to finally slow down. So your graph is not actually going to reach an angular velocity of 0. So now what's happening over the angular acceleration side, where this angular acceleration can be read as sort of a measure of how much friction there is. The more friction, the more negative acceleration you get. So as the friction is reduced, the angular acceleration is going to move closer and closer to 0. So they're not picky about exactly how you draw this. You could draw it more or less steep. You can have the line reach an acceleration of 0 before time t1. If it does, then you have to make sure that you don't continue the line up here. That's not going to start accelerating in the other direction. If the acceleration does ever hit 0, then it's just going to stay at 0 for the rest of the time. So any of these 3 lines that I've drawn would be considered acceptable for part C. All right, so there's one more part here, and this one might look a little intimidating. You're given a couple of equations here. So the first one looks like this, and the second one looks like this. And you're simply asked which one of these equations better models this experiment up above. So the thing to keep in mind here is that you don't actually have to derive or prove these equations. You're just choosing one over the other, and you have to give some sort of justification for that. And it turns out that there's just one simple test that we have to look at here. All right, so these are 2 candidate equations for the torque involved here. So we know that the torque is the thing that's slowing the wheel down, and as the oil starts to drip onto the wheel, the torque, the friction is going to become less, so the torque is also going to become less. So we should have an equation for the torque that starts to decrease over time. And by the way, I should point out that both of these equations are valid only for t greater than 1/2 T1. So this is the equation for the torque after we start dripping oil. Okay, so if we look at this first equation here, this is a linear equation. We have torque equals, some number times T minus C1 times T1, right? So you could rewrite the equation like this. So this just looks like y equals mx plus b. This is a linear equation. It has a positive slope and a negative intercept. So if we were to plot those, it would look something like this. So this does not show a torque that is decreasing over time. It's starts negative and goes towards 0, but then it starts becoming positive again. Whereas if we look at the second equation, here we have time in the denominator. So if you think about what happens as time increases here, as the denominator increases, the value for the torque is going to decrease. So this function is going to have some positive intercept. If we put t equals 0, then we have just some positive number over here. And then as t increases, the torque is going to decrease as well, and it's going to go closer and closer to 0 as time goes on. So this is the type of behavior that we want. This shows torque decreasing as the friction decreases. So equation 2 is the one that better models this experiment. And your explanation can be as short as just stating that this torque decreases as time goes up, whereas the other torque increases as time goes up. So the second one is what you want. Okay, so I hope this helped a little bit. If you still have questions, feel free to message me, and I will try to clear that up. All right, thank you so much for watching.